My internet friends, welcome back. We are on level 18. How many levels are there? It's 26, so we're almost done. We got a few more. Now, this level is called Magic Number, and this level was quite difficult for me. I came across the answer early on, probably like 40% of the way through, 30% of the way through, and I implemented the answer, got the solution, winner, winner, chicken dinner. But it took me about 60% of the allotted time I spent on this task, just understanding what in the hell the answer was and how they came to the conclusion of the answer, logically kind of reverse engineering it. So, that being said, this may or may not be a short or long video. We'll find out. All right, level is called Magic Number, and the level states that to solve this level, you only need to provide the Ethernaut with the solver, a contract that responds to what is the meaning of life with the right number. Easy, right? Well, there's a catch. The solver's code needs to be really tiny. I mean, really, really tiny. Like freaking really, really, really itty-bitty tiny. 10 opcodes at most. Hint, perhaps it's time to leave the comfort of your Solidity compiler momentarily to build this one by hand. That's right. Raw EMV bytecode. Good luck. Now, when reading this, I intuitively understood that we are not going to use remix for this level, at least not most of the time. Additionally, I obviously knew that they wanted us to write this in EMV bytecode based off of what they've stated, and there's 10 opcodes that we can use at most. So I don't know if we can do less than 10 or 10 is the exact number, all that. But in the end, our task is basically to input an address that allows us to provide the meaning of life back to this contract. So that's our challenge. And I don't think I have this code in VS Code, so we'll just quickly review the target code because it's like a few lines, and then we'll spend the rest of the time reviewing the notes and all the stuff that we've gone through. But before I do that, we got to go in the right order. We have to talk about the mistakes first. So where did I mess up, and specifically, why was it so difficult? Well, when first going through this process, I came across a few different types of answers. So one type of answer I came across was actually a series of Ethernaut challenges that were solved via Foundry, which is quite cool. So I started implementing this solution via Foundry, which is kind of like a hard hat, newer version of hard hat, where you can do tests and deploy to test networks via your console, your console and your also IDE and things like that outside of Remix. But with this solution, I had to learn Foundry from the ground up, which I learned quite a bit implementing the solution, but the learning curve was too steep and it took too long for me to actually just get through the challenge, and I didn't necessarily want to spend all of my time in this challenge learning Foundry when I should be learning the specific nitty-gritty details of the hack and why we were able to complete this. So that was my reasoning for skipping the solution and finding alternative solutions. So then I tried to look at Remix ideas, and none of that came to fruition because I'm not really sure anybody has solved it through Remix. And then I kept on iterating through different challenges, and finally I realized that all I needed was just a little logical thinking and the utilization of the console and the web browser, and I would have solved the challenge pretty straightforward. Those were the mess ups that I went through, and then I came across through a few solutions. Sadly, the blockchain Web3 developer YouTuber that we followed up to this point has actually stopped creating challenges after this point. I think until like maybe one level after this, but there's 8 or 9 levels that he didn't do after that. So it's us, the internet, and anything we can find on usually blogs and documentation. So luckily, this person here, 0xSage, wrote a pretty good resource to this challenge that I followed. And then listed in code questions, these two resources combined together helped me understand a lot more than what could be provided here. So these three kind of tied together helped me understand not only how the solution was created, but also how did they come about solving the solution in the first place? What was their thinking process? So those are some of the resources and some of the issues that I came across. I'll quickly click into some of these so you can see them, and I'll put them in the description as well so you can go to them. But here, this is the repo in GitHub where basically they've utilized Foundry to iterate through all the different solutions, or all the different challenges within Ethernaut, which is quite cool. And the next couple of resources, and I think I have them all open here. So let's close these out, keep that open for now. So Xerox Sage, as per usual, they did a great job at explaining the process, and that is not Xerox Sage. I don't know why it took me there. Weird. Must have saved the wrong thing. So we will open it up here then. So here you can see that this is actually level 19 for them because they did it so long ago in 2018. And you can see for us it's actually level 18. So we must have skipped a level, or the levels must have been removed as time has evolved. So they've done a great job at showing both good diagrams that I'll talk through in a second, and also giving you an idea of specifically how the solution was created and the importance of it. So that's always a good source. Another one is this source here from listed.to, so R1OGA, whatever that means. They have all three levels here, 16 through 18, so if you just skip down to 18, you'll see that they've written it out here. They've given some good explanations, good diagrams, good tables as well to walk you through specific opcodes and how those opcodes align with bytecodes, which we'll talk about in a second. So that was useful. And this resource here did another good job at explaining specifically how to construct the bytecodes and opcodes in a specific chronological order and why they're placed where they are and how they kind of coexist with each other. And that's what I think was missing here within this resource and this explanation, or at least didn't pop out to me as well as it came out to me in this source. So that's why I think when you kind of compile all three of these together, three of these resources, it comes out to being pretty understandable and hopefully intuitive in this video. With that being stated, there was a few links I wanted to share with you that were shared. Actually, probably just go to my notes and find them. Yeah, so Xerox Sage shared these two links here that had pretty good explanations on the general topics that are relevant for this challenge that I wanted to share with you because first off, this one is pretty straightforward and simple to read through. It's very basic on what opcodes are and how they kind of exist within the Ethereum ecosystem because it's very similar to many other computers, but they call out some of the nuances between Ethereum and other kind of basic opcodes. And then also this series here is really long and in depth, but it is worth the read if you're interested specifically in how to, as you can see from the title, deconstruct a contract and understand not just the Solidity code, but also the opcodes and the associated bytecodes with that and how all of it's constructed for a smart contract. It's, like I said, a long series. They have multiple parts to it. I've only gotten to the third part here. So I'm still reading through it, but it's definitely worth the read if you're interested in going that deep or at least having an intuitive understanding of how that stuff functions. So those are good there. And then also specifically in this multiple part series, they've actually created a really interesting chart that they walk you through throughout the entire series. So really quick, I'm not gonna, obviously this is way too tiny to explain. So what I'm gonna do here is I'm just gonna highlight some of the stuff here. So here is this little box here is your Solidity contract. It's gonna be run through a compiler and then it's gonna pop out into a series of opcodes. And these opcodes are going to be broken down into two chunks. So this entire thing is your entire contract and opcodes. It's massive, right? Well, we're going to break that into two segments. So we're going to have the creation piece, and then below that, we're going to have our runtime piece. Now, that's something that we'll talk about in a second and later on, but you'll know that anytime a contract is created, specifically has opcodes and different bytecodes and stuff associated to it, it's usually broken into two segments. So you have the creation part of the contract and you have the runtime part of the contract. Creation part of the contract is basically your contract being created via the constructor, and then the rest of the runtime stuff is all the additional information you put into the contract, such as the additional logic and execution and all that stuff. And this entire diagram is a synthesized snapshot of what that 5-part series walks you through and all the stuff that they kind of break down and really discuss in depth. So I think it's great that they've actually gone in to put so much effort into this to really try to explain the topic in a kind of a cohesive and narrative method. So kudos to the person that put this together because I'm sure it took a lot of work. All right, so that's kind of the mess ups and the resources that I found useful. The challenge is actually in relation to Hitchhiker's Guide to the Galaxy. If you're a nerd like myself or a big sci-fi fan, if you watched movies or read books, you'll know that the answer to everything in the universe and all that stuff is 42. In the Hitchhiker's Guide to the Galaxy, They waited 7.5 billion years to get that answer from a machine that they built. And the issue is they asked for the answer, but they didn't know what the right question was to ask. So the machine basically said, I'll be back in 10 billion years or something like that to give you the right question to ask instead of just the question you've asked originally. So it's all about the question, not the answer, you know? Very philosophical book. Okie dokie. So that's the challenge. Those are the resources. And now we shall quickly review the code, and then we'll jump into the notes to explain the solution. So here we have our compiler version. So remember, this is going to be changed to 8 if you want to put it in remix, and floating points no bueno. It should be static. Our contract is called magic num. We have a state variable here, which is a solver, and that's going to be an address. We have a constructor that's empty, and then we have a function here that's called setSolver. So this setSolver is going to take a solver that we provide it, and that solver is then going to be tied to this variable that we've set up here. So the solver is going to be an address that we point this function to, and the address we point this function to should respond with the answer to the universe and everything, which is 42. But remember, this needs to be less than 10 bytecode, 10 bytes. And to do this, we're going to have to make sure that whatever address that we create, whatever's in this address in this contract, is very, very, very tiny, and it only has what it needs. So when it provides this information back, it meets the requirements of being less than 10. So if that's the case, how do we think about this? How do we kind of like take a step back and think about, okay, how do we solve this problem? Well, when thinking about this problem itself and thinking about the solutions that I found, I really broke it up into 2 segments. So let's ignore this so we're not distracted by any of that. We'll start on this side because it's a blank screen. There's really 2 things that I thought about and that came to me when reading all these resources that really summarize what needs to be thought through to figure out the answer, and also figure out why the answer is the way it is. So the first is understanding specifically how is a contract created within the realm of opcodes and bytecodes. What happens when a contract's created and how that's broken up? Well, we've already touched on this, right? So there's one part, that's the creation piece. So we're going to create. And then there's another part, which is the runtime piece. So we know from previous challenges that the creation piece is actually 0 bytes. This is basically no. And we've done, I forgot which contract, I don't know if it was gatekeeper 1 or gatekeeper 2 or one of those, but I think it was a modifier in one of these gatekeepers here that we knew that was kind of the process. And the reason being is when you create a contract, it's really just going to run everything through the constructor, and that's all going to be run through the EVM, and then everything that's stored in memory that's executed on in the future is going to be associated to your runtime code. Now your runtime code is what we care about and what we want to make. We care about both of them, but this is the one that we need to make sure that's less than 10 bytes. So we know that the contract, when kind of run through the EVM and the bytecode and all that stuff, there's 2 segments. There's the creation piece and the runtime piece. So we need to think, okay, we need to create both of these to make sure we can pass the challenge. That's the first piece. Now, the next piece, we're going to scratch this out again, is going to be how do we actually think through what that would look like? What do we need to logically understand within the opcodes and stuff to have this contract do what we want it to do? Well, when thinking about it and reading through the solutions, really all you want to do is work backwards. So our goal here in the contract is to provide 42 back to this target here. Well, to provide 42 back to anything, we're gonna have to at least use a return opcode so we can return this value back to the contract once our address is called. That's one thing. Well, if we have to use the return, we know there's steps inside of this that need to happen. One of which is to store this information in memory so it can be returned and retrieved. So in this step, there's going to be more stuff that needs to happen. And inside of this step I'll talk about through in a second, there might be some stuff that needs to happen here. So when you think through this way, obviously I'm writing at a diagonal, I don't know why I'm doing that. We want to return something, we want to store it in memory, we need to probably do some pushing here and then some other things. So when you know that this is the case, these are the things that need to occur for us to provide this 42 back, we can reverse engineer that and say, okay, what are the opcodes for this, what are the opcodes for this, what are the opcodes for this, and then how do we concatenate them together to make to make the value that we want to make that's underneath 10 bytes. And that was kind of it was like an epiphany moment for me to realize, like, okay, these are the two segments and this is how it works. So hope that makes sense to you. Hope that high level explanation was useful. Now let's get into the notes. So in the notes, I have a bunch of stuff in here that I'm going to hopefully tell in a cohesive manner. This first thing here is basically saying, all right, our goal is to break into two sets. We've already talked about this. We have the creation piece and the runtime piece. And it has to be below 10 opcodes. Here is basically stating that the way that the compiler compiles code is it goes, so you write in Solidity, the compiler then converts that to opcodes, and those opcodes then are converted to bytecode, which then is read by the EVM itself, the machine, to do what it needs to do. That's kind of the logical connections here. This is a chart that was linked in one of the blogs that I came across that a lot of people actually refer to, is this table here, which basically shows you the breakdown between the opcode, the name of the opcode, and then the description of it, and then the associated gas for that. So this here, this is actually the opcode. I don't know why they're calling this the opcode, because this is the bytecode. So that's, I don't know why, it doesn't make sense to me. But yeah, this here is called the bytecode. This is the opcode, and that's the association between the two. And when you're thinking through the logical reverse engineering kind of process, you say, okay, if I know I need to return, then what does that look like? Is there a basic return? Yeah, we have a return here. So this is the hex for return, and this is the brief description of what's happening there. So that's useful. But in some of the other resources, they have more information that helps there. But you kind of have to do the back and forth of saying, I need a return, and what's encompassed inside the return, then I need those pieces, and kind of walking through that stuff. Below this is just another simple diagram that shows you the breakdown of the different pieces that I discussed already. This was, I think, in 0xAges blog. And then here you can say, that, okay, so you write your contract, and you write it in Solidity. That's then pushed to the EVM, which is compiled into bytecode, which this bytecode is then segmented into two pieces, and it's sitting on the stack, which we'll talk about in a second. And remember, this is the creation piece, this is the runtime piece. So the creation piece is associated to the constructor, and once the constructor does its thing and it runs through everything, the contract has its own address, then what you're going to do is you're going to store the different opcodes associated to your runtime piece of the contract inside of the EVM and Ethereum. So this can be called on in the future to have computations done to it. That's a pretty neat diagram that kind of gives you an idea of intuitively what's happening. So that's that. This next piece here is breaking down the creation step. So I have my notes, I have a bunch of notes here. So I have a creation step here, and then below here I have a runtime step that walks you through what's happening here. I'm going to reference this blog most likely because they've done such a good job at explaining it. But before we do that, I wanted to walk you through some interesting notes that I came across that help you understand a better understanding of how the creation segment of a contract looks like within bytecode, and specifically why it looks the way it looks. Now, here we can see that I'm basically regurgitating what I've already said. Now, this important piece here, there's this thing called a magic number within the creation of a contract, or creation of even functions, I think. And within a smart contract, this here is a magic number that you'll see a lot. And this number is the bytecode, right? So this bytecode magic number is indicating basically that and in the initialization of any contract, we want to do this thing called freeing a memory pointer. Now we free this memory pointer so we can actually do a few things. So we can write anytime after this point. So say there's a stack here, and before this, we'll say that there is a space that we've not touched, and then this location here is going to be our free memory pointer. And we're basically saying that anywhere after this point, we can store stuff in memory, and we can put different types of bytecode that we can refer to later. This free memory pointer, it needs to be set up initially when the contract's initiated, so we can then place items on the stack in different locations and understand the offset as well, so we continually keep putting items where they need to go, because every time you put something somewhere, that free pointer is then there, and then it's going to be there. And you need this so you can have the pointer pointing to the different locations in the stack so you know where to push information. It's kind of a high-level explanation to why that exists and what it's needed for and why this magic number is at the beginning of every single contract is because we need to have that free memory pointer for us to point around and push data and store data, etc. When you initialize a contract. Additionally, this is the sequence of what you would see most frequently. So what we're going to see a lot is actually this 0x60, 0x40, and 0x52. So 52 is referring to the stored opcode. The 40 here is referring to, I think, the position of where it's going to be located, and the 60 is referring to the size. This has been updated recently, so I think it was 0.5 or 0.6 of solidity. This has been updated to 80, referring to the size, 40 location, and 52 for the mstore. Just a random note that I came across. And then this is what it would look like in reality when you're putting this in the way that it's set up. And the reason it's set up this way is because it's reversed of what we see here. Reason being is that there's this thing called the stack. And within Ethereum, it's a stack-based machine. Now, let me take you down to a link here so I can just jump to that point and we don't miss it. This is a good Wikipedia article that walks you through specifically what a stack-based machine is and how it's designed and functions. And specifically, you can see in this example that I wanted to call out, it's a very simplistic example that says, okay, we have this expression, and we want to see what this looks like on the stack when it's placed on a stack-based machine. And we have a few mathematical operations that have to happen. We have an add, a minus, and a multiply. Well, if we look at this tree here, we also look at these opcodes associated to the numbers here, you can see that it's a last in, first out situation, where you have, say you have a stack of plates, right? The last thing that you've put on this stack is what you take off, and then the first thing you put on this stack is the last thing you take off, because if you take this plate out, everything's going to fall. So in the stack-based machine, you start at the top and you work your way down. Now that means that if you do it this way, you have to chronologically place items in the stack so you can take them out in a certain order. So we can see here that if this is the operation that we're going to run, we know that we're going to have to plus and minus first before we multiply, and plus as well. So if we look at this, we have our push. So our push is saying we're going to push A onto the stack. So we're going to push A onto our stack here. Then we're going to push B onto our stack. So we'll have B here. Then we're going to push C onto our stack. And then we're going to subtract, which is going to be here. What we're subtracting is we're going to subtract B minus C. So that's here, you can see this item here. So these are some of the first ones that were placed on the stack. So we're going to do B minus C, which is going to have a value here. And then we're going to do some more pushing. So we're going to push a multiply on here. So that multiply is going to be whatever this value is times A. So that'll equal a value here. And then we're going to push D and we're going to push E onto the stack, which is going to be here. And then we're going to do an add for those two. So we'll add those two together and we'll get the value here. And then we're going to do finally another add here, which is going to be the add here between those two values that we've derived. And you can see that it basically, the stack counts the leftmost equals the topmost recent. So meaning the leftmost here, you can see in this diagram, A is the leftmost, B, and then C. So that's how we've placed these on. And then we moved on to D and then E. And then we did the different types of multiplication, addition, etc. between each of those. And that's kind of how you can contemplate and understand the stack. And that's a very simple example that kind of gives you an idea of how things need to be chronologically based, which directly applies to how we're going to solve this challenge. And that's also, I went into that big long rant because you can see that when I've shown this example here, we can see that 80, 40, and 52 are reversed from what you can see here. And the reason being is that's the whole stack process, right? So we're going to first put on the load, then we're going to put on the 40, and then we're going to put on the 80. And we're going to do that because we need to do different things to each of these in a chronological order before this can be actually completed, because it needs these two values first. Hopefully that makes sense. Okay, so that's that. One other thing here is some people might ask, okay, so why did we leave the memory space between 0 and 40 empty? Why is that empty? Well, in the end, within Ethereum, we all know that there's a lot of hashing that occurs. Specifically, you have like the Merkle trees, right? So each thing that's hashed is fed up into the parent tree and the root, which is inside of the block. So a lot of the stuff, there's a lot of hashing occurring here. And this space is used for that hashing and also other variants of hashing. So it's just a thing that's needed for Ethereum to ensure that everything has some sort of credibility to it. And below here, One thing that you'll see for most of the free memory pointer segments, like the first part of the magic number, there's going to be a lot of this pattern here. So you're going to see a push, you're going to see a push, and you're going to see a store, which is exactly what you saw here. So you're going to get a push for the 80, a push for the 40, and then a store for the M store. And that's kind of the opcode. That's the opcode pattern that you'll see frequently with the magic number in the beginnings of most smart contracts. Here's just a brief example of that big diagram that I showed you. That between when you break this massive contract up, you have your creation phase and you have your runtime phase down here. And each of these segments have a beginning portion at the very beginning part of each of these opcode kind of strings or lists. And in the beginning of those, there's this little box here that's calling out specifically that these are identical. These are the same. And they're using the same thing that we've mentioned up here. It has the push, it has the push, and it has the store. It has the 80, 40, and then the 52. And that's identical because we're setting up that free memory pointer. And this is just one example you can see how this is utilized. Okie dokie. So we've done this. The next piece is code copy. But before I jump into that, so let's take a step back. We understand how a contract is initiated. We understand the two segments. So there's the creation and the runtime. We've talked through the magic number. We've done all that. So now that we understand all this, that's the first part of this. The second part is actually saying, okay, how do we figure out how to return 42 to our target? I'm going to jump to that, and then I'll come back to the initializing piece of the second part of the attack that we'll need to understand. So let's first focus on returning 42 after we understand the basics of how contracts are constructed and blah, blah, blah. So if we come down to this section here, the runtime piece, this is just a summarization of what I've already written out, so we don't have to worry about really any of this. Oh, pink, not black. We don't have to remember any of this because we've already talked through this via the drawings. All right, so we're good here. So I think what I'm going to do is I'm just going to jump to their explanation to show you specifically how they did it. And I think that's going to be the most intuitive way of explaining this. So in their explanation, they talk through some of the stuff that I've just mentioned above, just in a different manner. So we have some of the stuff of reverse engineering this. If we come down here, we can see specifically how they're going to walk through this. And I want to kind of hopefully explain this in a manner that makes sense. So this is the chronological order in which we need to put these opcodes together, because when you have an opcode, remember that you have an associated bytecode to that. And what you're going to do with all these bytecodes is at the very end, you're going to concatenate them all together, which is going to make part of our answer, part of our kind of response with the 42 that's written in bytecodes. So the way that these chronological opcodes should occur is listed here. So first, what we're going to do any of this stuff is we're going to need to meet the need of our return. So remember, we're going to work backwards from this. So in our return, we know that from the sheets and the things that we've read, we can see that there's a few things that are needed. We need the size of our value, and we need the position and the size. So this is the value that we're going to return, which is 42, and this is the size of that value that we need to return. So from that, we know that we need these items to return back. So if that's the case, then there's a few things that we're going to want to do. We're going to first want to figure out where we're going to store the stuff in memory, because remember, every contract initiates with a push-push memory store. So here we have a push, a push, and then a memory store that I mentioned previously. So this initial push is going to be the value of, I think this is 42 here. So 0x2a should represent the value of 42. So we've pushed our value there. We're going to push the position of where that value is located. So that value is going to be located at 0x50. After we've pushed that, and then we're going to store, so this is the storage piece, so we're going to store this value at this location in memory. So this is our memory store. So we have our bytecode here, here, and here. We're going to concatenate all those together. And then next, we're going to basically store the size of this value. So this 42 value is going to be 32 bytes. If I could write. And then this here is going to represent this here. So we're going to push that size there. So that's going to be push 0x20, which is 32 bytes. So that's going to be our bytecode. And then below that, we're going to push the position of this size. So the position of where this is going to be located is going to be the 0x50. And then we're going to return all this. So we're going to return our value, which is the 42. And then we're going to return the size of that value, which is the 20. So that's the process of putting all this stuff together. And then once you've done all that, you're going to concatenate it all up together, and you're going to have your string of bytecode here. And now the beautiful thing of this is that everything we put together is actually less than 10 bytes. And the reason we know that is because bytes are counted in increments of 2 bits. So each one of these digits is a bit, so 2 of those is a byte. So we have 1, 2, 3. Actually, let's zoom in. That's really crazy. All right. So if we count this out, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we can see all of this together is going to equal 10 bytes with a Y, which is 20 bits with an I. No, that's it. That's not an I. That's a Y. Bits. All right. So that's good. We've successfully created our runtime piece of the challenge. So we have a runtime piece. Now we have to create the initialization piece. So let's come back to our notes and make sure I didn't miss anything. I don't think I missed anything. So the next thing is we're going to basically go right back to that same blog and talk through their specific process of doing what they've done. But the first thing that we're going to learn from this summary they've provided is that code copy is going to be needed here. So a code copy is an opcode, and this opcode, specifically what it does is it copies your runtime code from the stack to memory, so it can be then used in the future for future execution when people from the outside world want to interact with your contract. That's usually the initial thing that happens when you create a contract, is you want to take that runtime code that you've created that does all the functions and stuff, take it from the stack, which is very ephemeral and dies off pretty quickly, and then put it on memory so it's it stays a little bit longer, which eventually I think should be put on storage. And here's just another link that highlighted that point that I've linked here, is basically showing you that the stack here is the most ephemeral, it changes the most, and it disappears the quickest. It's the cheapest on gas. Memory is the next step from that. So you want to take whatever you put in there and put it in here if you want to have future iterations of usage of that. And then eventually you're going to move it to storage, which is going to cost the most, and that's going to be the most expensive gas, and that'll be the utilized most frequently. And that's when you put state variables in contracts and stuff that can be utilized for your contract. And I think this links out to the same solution. Oh no, it links out to this. Okay, there you go. That's where that came from. Okie dokie. So with that being stated, let's jump into their explanation and let's talk through their initialization piece. So you can see that they've stated at the very top here that the opcodes that we're going to need here are going to be these. So we're going to need code copy, which code copy encompasses many of what you're seeing here. And that's what we'll kind of talk through as we walk through their logical explanations here. So one thing with using code copy is that, let's actually go through the definition really quick. I think they listed it out here. So the definition of code copy is what I've just explained. So you're copying the runtime code from the stack to memory, but there's a few things that are needed for that to occur. The things that are needed, the 3 arguments that are needed for that to occur, is where do you want to put that runtime code? So what's the destination of where this is going? Where is it currently located? Where is that runtime code currently at? And then what is the size of that runtime code? So we want to know, where are we going? Where is it coming from? How big is it? Those are the 3 steps we need for code copy. So now that we understand that, let's walk through this logic here. So if we look at this, there's a few things that are happening. First is we're going to push some stuff. So we're going to push the size of a runtime code. So remember, that's one of the parameters we need. We need to know how big is it. So the size we're going to push there is going to be 0xAA, which correlates to 10 bytes, which is how big our runtime code is because we've just counted it. And this is going to be our bytecode for that. Next to this is going to say, okay, where is this located currently? Well, we actually don't know where it's located currently, and that's why we're going to leave this as unknown for the time being, because the runtime code sits directly after our initialization code. Because remember how we talked through the contract where it had the big segments here? We had We had our creation and then we had our runtime. Our runtime, where it starts, is right where our creation ends. And we don't necessarily know how long our creation code is going to be until we finish this process. So for the time being, we don't really know what the position is of a runtime code at the moment, so we have to skip this piece until we finish the next. So that's the piece there. So we're gonna skip this for now, but we know that it's going to start with 6.0 because most of them do when it has a push in it. So the next thing here is, okay, where do we want to put this runtime code? Where is this going? Where's the destination headed? Well, what we want to do is we want to set it at 0, and we're setting it to 0 because we want it to be basically the start of our memory and the beginning of that. So we're going to set that to 0 for the start of our memory, so that's the first thing it hits. After that, we have our code copy, and this code copy is basically, this is the opcode for code copy, and it's going to take everything we've done up here and it's going to run through the execution process here. So it's going to take the size, where is it headed, where did it come from, all that stuff. After that, we're going to do another push, and the reason we're doing these is because we need to meet the requirements of the return. Because remember, we have to return, we need to return where this is located, so we then can kind of hit off of it and keep executing in the contract. So this return value needs 2 parameters. It needs the size, so how big is the value that we're returning, and where is it located? Those are the 2 things that we need, and that's what we're going to provide here. So we're going to push the size. So how big is this thing? Well, it's going to be 10 bytes. Remember, that's how big it's going to be. So it's going to be the same as above. So it's 0xa, 0xa. And then where is it located when we want to return this thing? And remember, we put it here. We put it at 0, which is going to be at the beginning of the memory. So that's where the position is going to be. So we're going to take these 2 things that we've established. We're going to place it into our return, and then we're going to return that back to whatever calls our address, which is going to be our target. So that's the logical connection there. So when you walk through all this stuff and you've concatenated everything together, you'll see that after you've concatenated these opcodes, that the length of this is going to be 12 bytes. And you can see that mentioned here, where, ooh, I didn't mean to do that. Exit. You can see they're saying it's 12 bytes in length, and that means that the position is going to be this. And we know that because, as we did last time, let's count this out. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's 12 bytes with a Y, and it's going to be 24 bits with an I, right? 2 times 12 is 24. So if we know that at the 12th byte here is where our runtime is going to start. So that means that we know the position of a runtime currently is going to be at 12 bytes, which is why they've stated this here. They said it's sitting at location 12, which means that it's going to be 0x0c, which is going to correlate to the value that sits there. So if we come down here, we'll see that they've specifically stated that this is going to be 0x0c, which is 60, yeah. So it's going to be 0c. That's going to be the position of our runtime. So now that we know that those are the 2 items, the next step is basically to put them together, right? So we have our initialization, our creation code, our initialization opcodes, our runtime codes. We're going to add them together, which is going to give us this long string of bytecodes, which is what we're going to shoot into our target. And the way that we're going to do it is we're going to do it basically how they've explained it here, and we'll walk you through that now. So we'll just basically take this answer here, and we're going to put it into a variable. So we're going to take that string, we're going to put it into a bytecode. So when we run this, it's going to give us back that bytecode that we care about. Then we're going to basically take that entire thing and then run it through a transaction. So what's happening here, we can quickly talk this through, is we're going to take whatever value is derived from this. Actually, let me make that a little bigger. Cool. All right, so we're going to do a wait like as we usually do. We're going to call web3 eth, and we're going to call send transaction, which is a method that we've used previously. And you know that if you go to the docs, you'll see what parameters are needed for that, and that it's going to come into a JSON format. This is something we discussed previously as well. So we're going to say, okay, we're going to send it from this location, which is our address as the player, and we're going to send this data, which is the bytecode that we've just created and took so much time to understand. So once we've gone through this, we're going to then place all of that information into this variable so we can use it later to get the contract address that's derived from the creation of this contract. So if we push enter, we're going to run through this here. All right, so this is completed, which is all good. We have our block hash. We have our contract address, which is what we care about and what we want. and we have from our address, all that stuff. Cool. So the next piece here is basically going to take what we've learned, and we're going to inject that into the set solver. But first, we need to set a variable. There's multiple ways you can do this, but we're going to do it this way because this is the way they did it, and it makes more sense. So we're going to take the contract address, which is what we've just called out here. So up above here, you can't see it, but there's a contract address that we just discussed. We're going to take that, and we're going to put it, we're going to call the contract address on here, and we're going to store it in the solver address. So we're going to put that in another variable. So now we have this number, which is what we called out here. So you can do this either way. You can just like copy and paste it from here and put it in the set solver, or you can put it in this variable to make it look fancy. Whatever floats your boat. And then we're going to take this, and we're going to do, we're going to take that variable, so that address that we just found, we're going to put it in the set solver, and then hopefully this will solve the challenge. And the reason this is going to work is because we're going to do exactly what it asked. We're going to put in an address that encompasses a contract that has the ability to return 42 in the size of 10 bytecodes. And if we can do that, we can give them the answer to the universe and everything and all that good stuff. So we will wait patiently for this to load. And once it does, then we shall submit our instance. And hopefully, fingers crossed, theoretically, that entire explanation would work. All right, so it completed the transaction. We're going to submit our instance. And hopefully, things go to plan. Boom, we did it. We completed the challenge, Internet. Happy Easter to you and me. You can see that level completed, congratulations, and you're the master of the universe now, congratulations to that. And also, I mean, we got to call this out because whoever created this has good humor. They're referring to, you got to give them your magnum look because you've done so good. You've completed such a difficult challenge. And I'm not sure if you know what the magnum look is, but let me educate you, Internet. That's the magnum look. If you've not seen, what is it, Something Blue Steel, you should see that movie. It's a good one. It'll make you laugh. With that being stated, we have completed magic number, and we are on to level 19, which is Alien Codex, which sounds quite intimidating. I'll see you there.